Hello everyone. In this video, we're going to be evaluating an interesting sum with even factorials. Actually, the reciprocals of those numbers. So we have 1 plus 1 over 2 factorial plus 1 over 4 factorial plus 1 over 6 factorial, so on and so forth, all the way up to infinity. And we're going to go ahead and find or evaluate this sum. Obviously, one of the questions that you need to raise is this convergent? Is there a finite sum for this series? So we're going to talk about that as well. And I'll be presenting two methods. I'll also show you some interesting results from Wolfram Alpha. This problem was inspired by a math competition problem. I don't remember where I saw this because I look at so many different resources. But in the problem, they were asking, I think it was in maybe a book. Anyways, let me not tell you what the book is all about because that's going to give away one of the strategies. But basically, it was asking the reader to prove something. So we do know what this equals. In the book was, the problem was basically phrased that way. But I just removed that so that you don't know what the sum is, and it's going to be hopefully more fun for those of you who are especially new to these kinds of things. So what do I mean by these kinds of things? I'm talking about the sum of reciprocals of factorials. So one of the things that you should definitely think about is these are evens, but we could also talk about the sum of all reciprocals of factorials. Anyways, let's start with the first method. Now, hopefully you do know that functions can be written as infinite polynomials. And usually we call them Taylor polynomials or Taylor series. You can make an expansion by looking at the derivatives. For example, if you look at f of x and set it equal to a function, you can basically evaluate f of x at 0, which is going to give you f of 0 equals 1. And then you can differentiate it and then evaluate it at 0 constantly. You keep doing this. And that's going to give you a bunch of values, right? But at the same time, you can make an assumption that this f of x, which is e to the x, can be written as a sub 0 plus a sub 1x plus a sub 2x squared, so on and so forth, as an infinite series, which we call a power series. Make sense? Okay. Obviously, power series are very powerful, pun intended, but we can use them even to solve differential equations. And I know some of you guys commented on the recent problems asking me to solve some types of differential equations. I'm going to try to solve them. But anyways, let's go ahead and take a look at this problem first. So we have this sum, and what does that have to do with e to the x? You might be asking, right? So I'm going to go ahead and give you without proof because we've done it quite a few times in other videos. You can definitely check them out online as well. And I'll just tell you that, hey, e to the power x can be written as follows. And this is significant because we'll talk about it in a little bit. So 1 plus x plus 1 over, I probably should write it together, x squared divided by 2 factorial plus x cubed divided by 3 factorial, x to the 4th divided by 4 factorial, and so on and so forth. Obviously, if you wanted to write the general term, you can kind of write it as x to the power n divided by n factorial. And of course, you have to pick n started at 0 because we do need x to the power 0 divided by 0 factorial. By the way, that is 0 factorial is equal to 1. Okay, that's for sure 1. It's not like 0 to the power 0 where it's debated. Anyways, I kind of have an obsession with that and everybody knows it. So this is going to be the expansion, the series expansion for e to the power x. But why is this important? Well, if you look at the original problem, we're supposed to evaluate the sum of the reciprocals of factorials, but they're only evens. 0 factorial obviously is not written, but that's what it is. So this should be helpful, right? The only problem is we need to get rid of the odd powers. And that can be done with a little trick or math trick maybe, or mathemagic. Okay, let's see. So I'm going to go ahead and replace x with 1. That's going to give me e to the power 1, which is e. And e equals 1 plus 1. You know that it's greater than 2, right? 2.7 something. By the way, I only know single digit after the decimal. Was it 2.72? Something like that. Anyway, it doesn't matter. And then this is 1 plus 1 plus 1 over 2 factorial plus 1 over 3 factorial plus 1 over 4 factorial, and so on and so forth. This will continue forever, right? And then, since I want to get rid of the odds, I should find a way to basically make those go away with a minus sign, of course. And that can be done thanks to the power of negative numbers being positive. We can go and replace x with -1. That's going to give us e to the power -1, which can be written as 1 over e. And then that's going to give us, by this, 1 minus 1. Notice that x is -1, and then -1 squared is +1, and -1 to the third power is -1 again. That's what I mean. So we're going to get something that alternates, and that's just awesome, because that's exactly what we want. By the way, you can think about what you would do, what should we do if we wanted to get rid of the evens and end up with odds, right? Something to think about, right? Okay, anyways, so these are the two sums, and they're both infinite sums. Can you add two infinite sums together? Sure. I mean, if you can add positive integers and get -1/12, I mean, by the way, that's incorrect, but anyways, that's a different story. In a video, I already talked about it. I mean, this should be done, right? This should be good to go. Anyways, this is what happens. When you add these two things, you know, the odds are going to cancel out. By the way, I'm not trying to say that Ramanujan was not a great mathematician. Absolutely, he was great. He was amazing, but, you know, he just got that wrong. Anyways, I don't know why I'm talking about it. Let's get back to work. E plus 1 over e is going to give us. Now, we're going to get 1 plus 1, 1 over 2 factorial plus 1 over 2 factorial. Instead of trying to add these, I'm just going to say, okay, you know what? I have this 1 plus 1 over 2 factorial plus 1 over 4 factorial plus ... twice. Because basically, we're adding that same thing 2 times. Make sense? Cool. We're so close. Oh, man. We got it. Almost there, right? This is what we're looking for, right? So we can go ahead and write it as follows. This sum is going to equal, oops, I forgot to put the infinity ... thingy. It's going to be e plus 1 over e all over 2, and that's actually e squared plus 1 divided by 2e. That should look familiar. Let's go ahead and talk about the second method real quick, okay? So stick around until we finish it. So for this one, I'm going to go ahead and use the Taylor polynomial for cosine. You know why? You might be like, why cosine, right? Because cosine is awesome, but that's not the only reason, because it has the even factorials. Isn't that beautiful? Now here, you might be thinking though, it includes the even powers, but with an alternating sign. I do need 1 plus 1 over 2 factorial plus 1 over 4 factorial plus 1 over 6 factorial. How do I do a little bit of hocus pocus so that the negatives turn into positives? Use your imagination. Maybe use an imaginary number like I, right? Exactly, that's what you need. So replace x with I, you get cosine of I equals 1 minus I squared divided by 2 factorial plus I to the 4th divided by 4 factorial minus I to the 6 by 6 factorial, so on and so forth. Notice that I to the 4th, I to the 4n is always 1, so this is going to be 1. And if you have a remainder of 2 mod 4, then these are going to turn into negative ones, and cosine I is exactly what we're looking for, right? So wait a minute, did we find something else? What the okay, this must be cosine I then, right? Yes, cosine I is real. Did you know that? Well, we did it in another video. I think it was on my other channel, maybe. I can't remember exactly, but a plus bi could be the other one, because that's about complex numbers. But anyways, cosine I is the same thing as e squared plus 1 divided by 2e. And you can actually explore that with this guy over here. This is Euler's formula. That's why Euler is just amazing. Not for this. Even if he didn't find anything else, it would be just amazing. The greatest of all times. And this brings us to the end of this video. Thank you for watching. I hope you enjoyed it. Please let me know. Don't forget to comment. Wait a minute, we're not done yet. Yes, I wanted to show you the decimal approximation, 1.543 something, and it's also called cosine hyperbolic, cosh maybe, and that's the alternate form is going to give you the value. And guess what? We can also find an infinite sum, but it doesn't include 1 in the sum. That's why we have to subtract 1 from it. And if you add 1 to this, you're going to get the exact same answer. Well, sort of, right? Exactly. And this brings us to the end of this video. Thanks for watching. I hope you enjoyed it. Please let me know. Don't forget to comment, like, and subscribe. I'll see you next time with another video. Until then, be safe, take care, and bye-bye.